Okay, so in this video, we're basically going over derivatives, also like voltage, electric fields, and how to, basically use them for the physics quiz tomorrow. So first here, we are asked to find the derivative of this expression 4x cubed plus 6 times 11x plus 2x to the power 4. So first thing we should notice is that these are multiplied by each other, and they're two expressions. So we have to use the product rule. And basically what that is it's you take the first one, let's just call this term u, and you find the derivative of that multiplied by, let's just call this v. Then you add it to the derivative, or you keep u the same, and then times the derivative of v. So basically this is what this looks like. So now we can just basically do that. So first step is derivative of this one. So this becomes, right, multiply, you get 12x, drop it down one, times over, squared, and then plus, what's the derivative of any constant? It's 0. So plus 0, right? Then we times it by v, and we leave it alone. So just times it by 11x plus 2x to the power 4, right? We have that, then it's plus, and then we keep the first term the same, 4x cubed plus 6 times, and it's v, derivative of v. So this is v, and we can derive it, so this becomes 11, because this is x to the power of 1, times, 1 times 11 is 11, and then drop 1 becomes 0, so this just becomes 11, and then this becomes plus 4 times 2, 8x cubed. And there is basically our answer. Okay, in the next question, we basically have this function of x, y, and z, and it basically says that the voltage at x, y, and z, a specific position in space, has the equation 5x squared y z cubed plus 2xy y squared z minus 4x squared z squared. And it is asking what the electric field is, the equation for it at the x position, y position, and z position. And we are given that in order to find the electric field, you just take the derivative of the voltage at each location for x, y, and z. So what can we do first? Well, let's start with our x, since that is first. So e to the x equals d dx of v. Well, what is v? We can put it in right here. 5x squared y z cubed plus 2xy squared z minus 4x squared z squared. Once we have that, we can actually take the derivative. So now here we have to be careful. So this is d dx. So this dx at the bottom shows that we are only doing it for the x variable, not the y or z. So in order to take this derivative for the electric field of x, we just focus on the x's. So what can we do? Well, this equals, so we see that there's exponent is 2 on the x, so bring that down. This becomes 10 times, drop it 1, x, and then you leave the y and z's the same, y z cubed, then plus. Here we can just remove the x and keep it 2y squared z, that's a z, minus 4 times 2 is 8, and then drop it 1, x and z squared. So that is the first one for the ex, right? You can just do that. Now ey equals the d dy of that same equation. We'll just write it down just to make it easy. Z cubed plus 2xy squared z minus 4x squared z squared. Okay, this equals, now we're just doing y because it's dy. So we keep 5x squared, and then y, there's only one, so it comes out, times z cubed plus, so you see the square, so bring that down, this becomes 4xy z, because you drop it by 1, minus, we see that there is no y here, so this just becomes basically the derivative of something that isn't there becomes 0. So this is just minus 0. And what does that basically just cancels it out? So boom, boom, and we're left with this for our y, electric field in the y. Finally, we have Ez equals d dz, and then let's write it out again, make it easier for ourselves. Y(z) cubed plus 2xy squared z minus 4x squared z squared. So this equals z has it's cubed, so bring that down. This becomes 15x squared, and you keep the y, and z goes down to 2, plus 2, keep the same, z becomes, it just gets out of here because there's no power, minus z has 2, so 8, keep the x the same, x squared, z drops to 1. And there we have our 3 equations for our electric fields. Okay, the next question asks, find the torque given that these 2 vectors. So this is a force vector and a r radius vector, and we have to note here that torque is equal to r cross f, and these are both vectors. So we can use the cross product here. So we are given the equations for both, and we can basically just plug it in. So it's matrices, right? So we have our main big one with I, J, K, and we basically first plug them in. So for our F, we can plug in 2, 5, and 9, and our R, we can plug in 1, 3, and 6, because they each correspond. This I corresponds to 1, J, 3, K, 6. Now, once we have our main matrix, we can actually do the cross product. So this equals the smaller matrix of I minus the smaller matrix of J plus the smaller matrix of K. And this will basically give us that torque equation that we're looking for, the vector that we're looking for. So first step, for I, we do 5, 9, 3, 6. 5, 9, 3, 6, because cross product. For I, you don't use the I. For J, you don't use the J. For K, you don't use the K. Minus, for J, it's 2, 9, 1, 6. And for K, you don't use the K. It's 2, 5, 1, 3. Now, we basically cross product. So how this works is you cross each one, and then you subtract 5 times, you do 5 times 6 minus 3 times 9. So 5 times 6 is 30, minus 9 times 3 is 27. This comes out to 3, minus, right, because there's a minus sign. 6 times 2 is 12, minus 9 times 1 is 9. This also comes out to 3, plus 3 times 2 is 6, minus 5 times 1, so 6 minus 5. This comes out to 1. So now we just put it all together. 3i minus 3j plus 1k. And we can do the little hats that Heidegger loves. And basically that is our equation, and then we have to put units. Don't forget units, and it's Newton meter. And that is how to do a cross product.